This video will move into section 3.5, which discusses a summary of curve sketching. Our book has quite a lengthy list of items that we're going to look for in order to really put together a good full sketch. We're still sketching, so this isn't going to be perfect, but it'll still include a lot of details to really give us a good overall picture. And if you read through your book, I believe it's about an 8-step process with all the different information. They go through, they want to look at the domain, the intercepts, they want to talk about symmetry, they want to talk about asymptotes, increasing, decreasing, local max mins, concavity, points of inflection, all that to sketch the curve. So that is quite a lengthy list. I think we could shorten that a little bit. I think it's easy enough, and this includes all the components of what they're talking about, if we simplify curve sketching by looking for 4 major components. We will look for, number 1, all the important intercepts. We'll get all of the important spots where we're crossing and touching all the axes. So now, of course, intercepts, that's one quick word to describe our first step, but to realize, as I just said, we're going to talk about both the X and Y intercepts. So I'm kind of listing that as step 1, but we're really getting 2 very big pieces of information. Now, step 2, we'll look to find any asymptotes. Now, the book does mention slant asymptotes, but we're really going to stick, and this is kind of like the previous, we'll just really consider the possibility of both vertical asymptotes and horizontal asymptotes. But now realize what is involved with doing this. To think about vertical asymptotes, we're really thinking about setting the denominator equal to 0, right? We talked about this way back when we looked at continuity. So looking for the discontinuities, but specifically looking at where those discontinuities shoot off to positive or negative infinity. So by doing that, we'll actually be looking at domain. So like I said, this is a slight shortcut. By thinking about vertical asymptotes, that'll force us to consider the domain of the function. And similarly, when we talk about the horizontal asymptotes, to look for those, to search for those, even if we don't find any, we'll have to take the limits as x approaches both positive and negative infinity. So even if we don't find a horizontal asymptote, we'll still get the function's end behavior. Okay, so you're already seeing, I'm listing 2 steps so far, but there's a lot of work to get those 2 pieces. Step 3, we'll keep going with this. Unfortunately, now I can't get away with this with one word. Step 3, we'll consider where the function is both increasing and decreasing. And as we've seen from one of the previous videos in 3.3, once you know the ups and downs of the function, you're basically getting the relative, the local max and mins by default. Going up followed by going down will force a peak, will give us a max. Going down followed by going up will force a valley, will force us to have a minimum. So again, 2 big pieces, but while we do that, we'll basically get the local max and mins by default. And similarly, step 4, we'll finish with a discussion of the function's concavity. And similarly, like once we know the increasing, decreasing, we'll use the first derivative for that, and we'll get the local max mins. We'll use the second derivative to discuss the function's concavity, find where it's concave up, concave down, and while we're doing that, we'll also get the points of inflection. So that's quite a lengthy list here. So we're going to do that with one problem, but before I get so caught up, I want to remind you how much of this comes from section 3.3, and I want to break this down and just look for smaller components. When you get into the homework in this section, again, they throw the kitchen sink at you. Most of the problems, they give you a function. They want you to get all this information to put it together. So you'll see in a few minutes, even with a simple function like this, that is a long list of work. So thinking ahead for a test, again, the homework is good, forcing you to do all that, gets you a lot of practice and puts it all together. But on the test, you should basically expect separate components. You should expect questions that just focus on increasing, decreasing, that just focus on end behavior and horizontal asymptotes, that just focus on concavity and points of inflection. And then when I want you to focus on the curve sketching, I'll give you the information and ask you to put that together. And that's what's been happening in the earlier sections. So after we finish this section, you should be able to go back on some of those earlier problems where they just told you stuff about the first derivative and asked you to sketch the function. Or they told you stuff about the first and second derivative and asked you to sketch the function. They're not giving you all of these pieces, but they're giving you enough that we can do some decent sketch work. Okay, so like I said, we'll come back and do all of this, but let me just jump and let's get some good reminders from what we've already been doing. So this will be the second page, and let's look at the function g of x equals the quantity 6 minus 6x to the 2/3 power. And for this one, all I'm going to ask is where is this function g of x increasing, and then separately, where is this function g of x decreasing? So those are my two questions for this function. So a good reminder, again, all this stuff, 3.3, we said it when we were going through multiple videos that went with that section, because that really has so many of the questions that come up big picture in this chapter. So seeing a little more here. So increasing, decreasing, well, without having the graph in front of me, only having the equation, I'm going to need the first derivative test interval. I'm going to use that theorem where the derivative is positive, the original function is increasing, where the derivative is negative, the original function is decreasing. And to know where the original function is increasing, decreasing, where the derivative is positive, negative, well, first let's take the derivative. Nothing too crazy here, just a little chain rule. 2/3, 6 minus 6x to the negative 1/3. That's the derivative of the outer, leaving the inner intact, times a negative 6. There's the derivative of the inner. I hope you realize, everybody, while you're doing 3.3, if you make mistakes taking your derivative or your second derivative, then you end up with equations that you can't solve easily. It really, really spirals downhill pretty quickly. So again, careful work with our derivatives. And if you end up with equations that seem ridiculous, how are you supposed to solve them? It's very possible you just made a mistake taking your derivative. So, took a good derivative. I'm going to clean it up a little bit. 2/3 times negative 6 will give me a negative 4. This negative exponent, I'm going to take that whole expression, move it to the denominator to make it a positive exponent. And now I'm going to find my critical values. Where does this derivative equal 0? Well, it's a fraction. Negative 4 doesn't equal 0. But then I also need to look at where the derivative doesn't exist. And this does have a denominator. So that'll get set equal to 0. Technically all to the 1/3 power, but we've seen that a bunch of times. Just the inner part is enough. If you add this to the 1/3 power, you'd cube both sides, and 0 cubed is still just 0. So I'll end up getting, subtract the 6, divide by negative 6. We'll get x is 1. So nothing too crazy here. Only one critical value. And I'm just going to test the derivative before and after. So before 1, I'll use 0. Technically, I'm plugging in everywhere. And again, I could plug in up here, just a little easier. I like my cleaned up version. And this was, as soon as I cleaned it up, right, when I was solving, there was no need to factor. It was all already nice and neat. So now plugging 0 into that version. Well, the top is negative 4. In the bottom, 6 minus 0 is positive, positive 6. The cube root of 6 is still positive. So a negative divided by a positive will give me a negative. Go to the other side. I'll use x is 2 for the other interval. Well, the top is still negative. It's always negative 4. There's no x there, so that's always negative. But now in the bottom, 6 minus 12 is negative, and the cube root of a negative is a negative. So a negative divided by a negative, we end up with a positive. And that's it. Only one critical value, so we only had 2 intervals to test. Now I can come up and answer. The negative part of my derivative is where the original is decreasing. So this interval, negative infinity to 1, would be the decreasing interval. And then where the derivative is positive, the original is increasing. So only one interval here. We'll get 1 to infinity is where my original function is increasing. So that's the question I asked. I'm done. Just before I move on and do a second one and focus on one of the second derivatives, just again, a good reminder. If I said to you, what are the critical values of G, classify as local, max, min, or neither, it's the exact same work. There's the work for the critical value, and then technically this was the first derivative test, but this was a very good way to figure out if this value is a max or a min or a neither. You're going down, followed by going up, that's a minimum. Okay, so now let's do a whole new problem. And just to realize, if you are asked to sketch this, well, if you only had this information, there's a bunch of things that could happen. You just simply would be going down before you get to 1 and then going up afterwards. So something like this, or something like this. I mean, all these are possibilities, but if that's all the information I have, there's a lot more possibilities. When we get lots more information, now we'll know more to know, well, is this exactly it? Does it flatten out on the extreme ends? Does it go up? Maybe, I mean, this, if I just do this, this is very basic, concave up. This one, I had concave down, concave up, concave down. Maybe it's more like this, and it's a sharp point. So again, only having a little bit of information gives us lots of possibilities, and that's why in those earlier sections, there wasn't just one answer. As long as your sketch satisfied the information, you were correct. Okay, so moving along, let's do another one, and now let's focus on the function h of x, and we'll have h of x is, we'll have 12x to the 5th power, plus 15x to the 4th minus 120x cubed. And in this one, I want to ask, where is my function h? We'll do concave up. And where is my function h? Concave down. Okay, increasing, decreasing. We used the theorem that connected the first derivative and the plus or minuses to the original being increasing, decreasing. Now I'll need the second derivative test interval where the second derivative is positive and negative will tell me where the original is concave up, concave down. So I'll need the second derivative. Well, first thing I need is the first. Simple function, nothing too crazy, addition, subtraction. So I'll go quickly, 60x to the 4th. Plus 60x cubed minus 360x squared. And that allows me to quickly go right into a second derivative. What is that? 240. Oh, I'm sorry. I picked the wrong problem here, everybody. I'm sorry about that. Let me fix this. I still want to ask the concave up, concave down, but I just had a little goof in that problem. Let's just pick a different one here. Let's look at 1/12 h of x is 1/12 x to the 4th minus 1/3 x cubed minus 4x squared plus 7x. I'm sorry, everybody. Again, as I was mentioning, just the idea of taking these derivatives setting equal to 0, that one was not going to work nicely. That one would have worked nicely for the first derivative for an increasing, decreasing, or a local max min question, but that was my fault. I just picked the wrong problem. So here's my h, concave up, concave down. First derivative, 4 times 1/12 is 1/3 x cubed. 3 times 1/3 is 1 x squared minus 8x. And then a second derivative, 3 times 1/3 is an x squared. That'll give me a minus 2x and a minus 8. I need the important spots where the second derivative is 0 or undefined. Not to worry about the undefined. Here we did have a denominator, had to think about denominator 0. Here we could just focus on the numerator. Little factoring. Two important spots. And now I'll, again, set up my test interval. Over here, I'll use -3, negative, negative, gives me a positive. In between here, I'll use 0, negative, positive. gives me a negative. I'm going a little faster this time. I hope you've had some practice. So this, again, shouldn't be, we don't want to rush through it, but it shouldn't take us too long with a little practice. So out here, x equals 5, positive, positive, gives me a positive. So the concave up goes with the positive second derivative. So I'm getting two intervals here. This one, negative infinity to negative 2, and this one, 4 to infinity. And the negative second derivative goes with concave down. So we just get negative 2 and negative 2 to 4. I asked about concavity here, but just to realize, if I said, where does H have points of inflection? Same work. The important spots, check the concavities, and now we just be looking, are we changing signs? Up here we talk about, well, do we go up to down or down to up to figure out max or min? But here, as long as we change concavity, and we change concavity in both spots. Right here, concave up to concave down, negative 2 would be a point of inflection. And same thing here, concave down to concave up, 4. Remember, if I just say where, that's all you need. X is negative 2, X is 4. When the book tells you to find the points of inflection, you'd have to go back and then get the Y's to go with it. Oh, I'm sorry, when I was taking my derivative, I missed the plus 7 here, and then a 0 here. Okay, so now, let's get back to this first problem. Because you saw, again, handling one at a time, but now trying to handle all that information, there's a lot there. And I'm even adding more to it. So let's take our time and go through this. First thing, get my intercepts. Well, if I want my x-intercepts, I plug in 0 for y, solve for x. So solving this equation, I'd factor out an x cubed. And I get 2 answers. And then formally my x-intercepts would be 0, 0, and 4, 0. My y-intercept, well, notice the origin was one of my x-intercepts, so by default, that's my y. But starting from scratch, plugging in 0 for x, and we get 0 minus 0 equals 0. So again, just confirming what we had. For asymptotes, well, we'd look for vertical asymptotes, but there's nothing in the denominator. There's no discontinuities to consider, so there would be none. And by the way, that also clarifies for us the domain. There's no issues here. So this would have a full domain, negative infinity to positive infinity. So even if I don't make that note, that's what I'm kind of figuring out when I do this. Similarly, when I think about my horizontal asymptotes, I'm going to take the limit of my function as x approaches the infinities. So when we did that work, we talked about dominant term. There's no top and bottom here, there's just a top, so I'm just going to look at the x to the 4th. And for this one, well, a huge positive number to the 4th power is still a huge positive number, but even a huge negative number to the 4th power still gives me a huge positive number. So I did not get a horizontal asymptote here, but I did get my end behavior, that on both extreme ends of the graph, as x goes to negative infinity, my y is going up to positive infinity. I'm getting this type of end behavior. And similarly on the other side, as x goes to positive infinity, the extreme right, the y's are also going off to infinity. So again, I looked for asymptotes. I didn't get any, but look at how much other information I got. I found a full domain, negative infinity, positive infinity, and I got my correct end behavior. And now we really get to the calculus stuff. Technically, this was calculus stuff as well, but the deeper calculus stuff, I need a first derivative equal to 0. 4x squared comes out, x minus 3 left behind. I'm getting 2 critical values here. Especially here, I've always kind of stressed it's a good idea when you make these test intervals to always keep track what you're testing, and that here I'm testing the sign of the derivative. But especially now that we'll have both first and second derivative information, just want to keep yourself nice and organized, nice and neat. So before, I'll use -1, I get positive negative, which is a negative. Then I'll use x is 1, positive negative, which is still a negative. And then x is 4, I'll get positive positive, gives me a positive. Decreasing, still decreasing, and then increasing. And honestly, for some people, that's enough. They don't need to write anything else out. When we go to actually start sketching, once we put all this together, for some people, just looking at this chart, that's enough. But again, a lot of us like to just make sure we translate that. So again, my original function is decreasing on these two intervals, but then my function is increasing just on this one. And again, local max mins, that's a neither, that's a min. Getting all that, we had the first derivative test interval, and that immediately tells me down, still down. Again, that's just a flat spot, but over here, down and then turning up, we're getting a valley. That makes that a min. Second derivative, because now I want the concavity. Go back up here. Don't take another derivative here and use product rule. Make your life easy. Go right back to here. 12x squared minus 24x. Again, where is that 0 or undefined? Well, nothing to worry about undefined. 12x comes out, x minus 2, x equals 0, x equals 2. Second derivative test interval, -1, negative, negative, gives me a positive. +1, positive, negative, gives me a negative. And finally, x is 3, positive, positive, gives me a positive. So my second derivative test interval tells me my original function is concave up, here and here, -infinity to 0, and 2 to infinity, and that my original is concave down here, 0 to 2. And therefore, both of these points would be points of inflection. Just going backwards for one quick moment, that's not that uncommon, everybody, that if you had a critical value that ended up being neither a max nor a min, I don't want to say it always happens, but it's fairly common that that point ends up being a point of inflection. And again, that's not a guarantee, just something that's a little bit of a common trend. So now let's put that together. How do we put all this together? Well, the reason I put these steps, we could have found these in almost any order as long as we had all this information. But kind of the reason I did this is because this is how we should put it together on our graph. Get the important points marked off, get the asymptotes marked off, and think about end behavior, and then start drawing. Follow the ups and the downs. Go in the most natural way possible, and then when you're done, we should double check our work by making sure the concavity matches. This is almost kind of the proof that as long as nothing funny happened, that everything should kind of naturally match up here to kind of show us that everything came together appropriately. So let's see that. Couple of important points, the origin, and 4, 0. All right, that already had my y-intercept. We didn't have any vertical or horizontal asymptotes, but I know I'm going to start up here and finish up here. That's that end behavior. So I'm starting. Let's start on the left side. So I'm starting somewhere over here. And even though this kind of starts this idea of going up and left forever, but now I'm going to move myself to the right. And kind of naturally, if I'm going to start up here, the only way for me to go is to start by going down, but I'm really going to the increasing, decreasing. I'm just going to follow what this tells me to do. So I'm going down until I get to 0, and then I'm still going down afterwards. But 0, we kind of stopped and flattened off. So I'm going down, right? I started up here, I'm going down, but as I come to 0, my derivative was 0 there, so I do flatten off, but then I continue to go down until I get to x is 3. Still a sketch. I mean, this is where we could add more to it. We knew 3 was a local min, so if we really wanted to know exactly how low that min was, we'd use the 3, find the y to go with it. But again, that's part of this just being a sketch. So now we got to here, going down, flattened out, but then still kept going down. Now I'm at 3, and now I go up. And now as I go up, I hope you noticed, I was going down, but I wasn't going down blindly. I hit this point along the way, and now I'm going to hit this point along the way. So I'm going up, hit this point, and that's it though. I keep going up forever. So I go up, that matches, there's nothing else that happens. That's the full extent of the graph. That matches the end behavior, especially the right side. We use this to get started, but that matches. That's a nice little confirmation. But the last confirmation that everything came together well is this. Look at the picture. And now maybe every once in a while we have to just slightly smooth some things out a little bit. But now look at the picture. We should be concave up from forever left until we get to 0. And basically, again, maybe we want to just smooth this a little bit here so that we get more of that U shape, that it's a little more clear here. But yeah, that is concave up. And then from 0 to 2, so from here to here, we're concave down. And yeah, again, it's the half. This is the half concave up, and this would be the half concave down. And then from 2 to infinity, so from here on, we're back up. We always said the points of inflection, it's a little hard to say exactly where does this switch from concave down to concave up, but it's definitely in this ballpark, so that confirms everything. That's a good sketch. Now, that was certainly not easy, and as we kept saying, all this work to just sketch one function. And if you go to the examples in the book and the homework, that's mostly what they're trying to get you to do. So again, a lot of good practice. But we really should also just make sure we're getting the practice with just the sketching. So for these next two, and very probably what will happen on your exam, I'll just give you information. I'll give you information, and then you sketch the graph based on that information. So let me start off. Let me start off by giving you some information about function, we'll call this one function A. So our directions will be sketch the function based on the given information. And number one, we'll look at A of x, and what is it that we know about A of x? Well, we're going to say A of x has intercepts -3, 0, 0, -1, and 1, 0. Okay? I'm not telling you x or y. We should be able to look and go, oh, those are the x, that's the y. So that's just given. The next one, I tell you that the limit of A of x as x approaches positive and negative infinity equals 1. I will also tell you that the limit as x approaches -1 equals negative infinity. And then we'll finish up with A prime of x is less than 0 on the interval -infinity to -1. A prime of x is greater than 0 on the interval -1 to positive infinity. A double prime of x is less than 0. This one will have on the interval -infinity to -3, union 1 to infinity. And then we will have A double prime is greater than 0 on the interval -3 to 1. Okay? So, a lot of information here, but we need to be able to sort it. Again, I told you intercepts, but to distinguish the x's versus the y. When we come over here, we're getting limit information. Retranslate this. As x goes to the infinities, the function goes to 1. That's the same thing as saying we have a horizontal asymptote, y equals 1. The limit as x approaches -1 is negative infinity. Well, now you're focusing on an x value that's shooting down forever. That's giving us a vertical asymptote and pointing out we got a little hole. Over here, the derivative information, less than 0, the derivative is negative. Greater than 0, the derivative is positive. This is talking about where the original function, is decreasing. And this one would be where the original function is increasing. And then similarly, the second derivative is less than 0. That's talking about that the function is concave down. And then that a double prime is greater than 0. The second derivative is positive, tells me a is concave up. So I gave you a lot of information, but we still kind of needed those theorems to be able to translate and put the ideas together a little bit. And now, like the previous one, let's make our sketch. Let's see what happens and make sure everything looks good. So I've got my function. There is the horizontal asymptote. There's my vertical asymptote. These points. There's -3, 0. There's 0, -1. And 1, 0. So I'm starting out here, but I'm either above the asymptote. This is what horizontal asymptotes are, their end behavior. I'm not starting up here. I'm not starting down here. So I'm starting and I'm either going up or I'm going down. We'll use the increasing, decreasing. The first interval tells me I'm decreasing until I get to here. So I've got to start here and I'm going to go down. Not just blindly going down, hitting this point, still going down, approaching this asymptote, but I know I'm going to -infinity, so I'm down here. And now on the other side, well, I either start on the asymptote either down here or up here, but look what I need to do. I need to increase. Well, if I start up here, I can't go up. I have to start down here. And if I'm starting down here, I'm going up. But while I'm going up, I hit this point, right? I mean, this is it, everybody. This only 2 intervals. I went down and I hit my points along the way. Now I'm going up. I'll hit my points along the way. And now I'll just double check my concavity. And now I should be concave down from -infinity to -3. Actually, I'm so sorry, everybody. I have a problem written down and I just miscopied. I'm so sorry. I just did that again. So I wanted this to be concave down on both of these intervals. This was concave down to -1 and then -1 to infinity. I'm very sorry about that, everyone. But that's the initial parameters I wanted. So this function was never concave up, and I'm very sorry. Now that we look, that's exactly what we see. That definitely is concave down, the half, the downward U, and then this is also concave down. Again, the little bits as I hit my points, maybe just, we accidentally had a little extra bend that we want to work out so that we see that's a little bit smoother in that half of the upside down U, but that is definitely a good picture. Okay, and one more, everybody. Let's finish up. Let's look at number 2. And just like before, I'm going to just give you a bunch of information. And this one, I'll even try and be a little more clear with this. And again, I really apologize that I miscopied that. But now let's look at b of x. And b of x goes through, and let's have -3, 0. And then -1, 0, 1, 0, and 0, 1. Similarly, you look carefully. Here, I want x-intercept, y-intercept x. Here it's x, 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 and then that one's y. But again, we should just be able to look and tell, so I'm getting my intercepts here. And then I just want to spell it out. I just want to looking at my increasing, decreasing, before I tried to hide that information a little bit. Oh, I'm sorry, just to tell you, so the domain of B is all real numbers. Well, that tells us that there's no vertical asymptotes. A vertical asymptote needs that discontinuity. So it kind of seems like, well, what's the big deal? Well, everything, there is a domain everywhere here, so we won't have any vertical asymptotes. And then I will tell you that the limit of b of x as x approaches negative infinity equals positive infinity. The limit of b of x as x approaches positive infinity is negative infinity. No horizontal asymptote this time, but I'm still getting my end behavior. The extreme left, I'm starting at the top, and the extreme right, we're going down, right? We'd have like this up left end behavior on this side, and this down right end behavior on this side. That's what this information will be telling me. And then I just tell you, b of x is increasing from -2 to 0 on the interval -2 to 0. b of x is decreasing on the interval -infinity to -2, union 0 to infinity. Just coming right out and saying it, not using the b prime is greater than 0 here or b prime is less than 0, just showing you it, and that's that. And now let's finish with some concavity. Let's get that b of x is concave up on the interval -infinity to -1, and that b of x is concave down on the interval -1 to positive infinity. So I'm going to come up and use this space. So we had all this for the a function, and now we got all this for b. But just like before, get all the initial stuff on here, get my points, -3, 0, -1, 0, 1, 0, and 0, 1. Full domain, so I don't have any vertical asymptotes. Again, no horizontal asymptote, but I know I'm starting up here. Just one little thing, everybody. This is my first important point. I don't have so much room on my paper, but don't start way out here. You don't want to get extra bends. Just start closer. So I'm just going to start this far left side is really just going to start me up here. But what happens from here? Again, increasing, decreasing. All the points and asymptotes here, and get yourself at least initially started, but now follow your intervals of increasing, decreasing. The first interval starting from the left, decrease until I get to x is -2. But in order to decrease until I get to here, I got to hit this point along the way. So I'm going to hit this point and keep going down, but I'm preparing because I know I'm going to switch at -2, and then if I decrease to -2 and then increase after, well, now I got to swing back up. So now as I swing back up, I'm increasing until I get to 0. So I'm increasing until I hit this point. We actually had a point at 0. So I'll just increase and do that. Last interval. I'm decreasing for the rest of the graph, 0 to infinity. So I'm going down from here forever on. Well, I got to hit this point along the way. And now I'm going down forever. And that down forever on the right side matches the end behavior we had here. So that's already a nice confirmation. But ultimately the concavity. I'm concave up, -infinity to -1. And there's the nice up shape until I get to here. And then I'm concave down from -1 forever to the right. And that's the perfect. I'm not even getting the half U's for concave up and concave down that we had here. We're getting the full U up and the full U down. So, not the easiest thing, everybody. Like I said, a lot of work that comes from 3.3, a few ideas that came from 3.4, and this section is trying to get us to pull it all together. But now that we've seen the sketching, even if we don't have all this information, if we just have pieces, we should have a much better idea to go back and do some of the basic sketching that the book was asking us to do earlier. And again, hopefully this gives you some good ideas as far as how to put the sketches together in the homework in 3.5.